We end Chapter 7 with a discussion of distributed forces. Many net forces are the result of distributed loads over surfaces or volumes. The flow of air over an airplane wing creates lift based on the difference between the distribution of pressure on the bottom and top surfaces of the wings. Pressure is normal to the surface, but there is also a frictional surface load from shear stress tangent to the surface. The shear stress develops because the air flowing over the wing grabs the wing and must move with the plane's velocity at the wing's surface. The air then transitions back to zero velocity, moving away from the wing. We call this transition region a boundary layer, and the strength of the shear stress depends on the air's viscosity as well as the sharpness of the transition region. This frictional shear stress, combined with some other effects related to the way the air navigates the wing as it moves past it, is what's responsible for the drag force. We also use the word traction to refer to surface loads, so there may be normal tractions, as in pressure, or shear tractions, as in friction. We also have body or volumetric loads, the most common being due to gravity. Here the distributed load is volumetric mass density ρ times gravitational constant g. Integrating over the body's volume gives us the weight as the integral over the volume mass density g dv. Line loads are not so much physical as constructions from surface or body loads for specific applications. One set of problems of great interest to civil engineers is the behavior of structural beams under lateral loads. Look at any tall building in the early stages of construction, and you'll notice a latticework of beams. Vertical beams, columns, and cross beams between columns. The cross beams, in particular, are subjected to a combination of distributed loads from their own weight as well as surface loads from the floor they are supporting. These gravitational loads are perpendicular to the long axis of the crossbeam and are sometimes referred to as lateral as opposed to axial loads. The interesting part of a crossbeam's behavior is its lateral deformation along its length and the stress that induces in the beam. Instead of working with weight as a body load, we multiply the body load by the cross-sectional area of the beam to obtain a line load. Here we're going to use the symbol W again, but this is going to be a lowercase w. It's going to have units of newtons per meter, and this will be equal to mass density ρ times g, that's the volumetric body load, times A, where A is the cross-sectional area of the beam. And for this particular beam, for instance, if it's an I-beam, then the cross-sectional area would be the area of this section, looking at the I-beam from this direction. In many cases, the line load is just a constant, because beams often have uniform cross-sectional area. In some problems, you may see a step increase or decrease in line load along a beam corresponding to a changing distributed load beyond the self-weight of the beam. It is also possible that the line load could be a function of position along the beam. If we go back to our airplane example and look at the airplane from its nose, then each wing looks like a cantilevered beam built into the fuselage. If we look at a wing from this perspective as a beam, it's a beam with a tapered geometry deep at the fuselage and tapering to a much smaller width at the end of the wing. If we replace the pressure differential with a line load by multiplying through by the thickness or depth of the wing, then with a uniform differential pressure, the line load will be high at the fuselage and taper to a smaller value at the wingtip. Because of the range of application of line loads, we will have to be prepared to address problems where W is a general function of position. This last section, 7.4, is divided into two parts. In the first part, we address line loads, and in the second, we address pressure loads for a very specific kind of loading: hydrostatic pressure on submerged surfaces. As you might imagine, there is a much wider variety of load distributions we could examine, but this falls into the domain of different disciplines. Those of you pursuing civil and mechanical engineering will eventually get plenty of exposure to these additional topics, so for now we'll restrict ourselves to just these two topics, beginning with line loads. For the purpose of finding reactions it supports, we can replace a distributed line load with its resultant force acting at its effective center. This is just another manifestation of the center of gravity calculation we did in section 7.2, which in turn was an application of equivalent force systems from chapter 4. It states that the effective center of the line load is based on a force-weighted average of position. Before finding the effective center, we may have to construct a functional form for W of x. This is important in many applications, including finding the internal forces and bending moments in beams in Chapter 8. Here we have a first example that provides a description of the distributed load acting on a beam. We have to use this information in the problem statement to construct W of x. We are told that this beam supports 160 chocolate candy bars, each weighing 1 pound. We will put aside the fact that even one of these bars could induce a diabetic coma. The first piece of information provided by the problem statement is that the integral of the line load over the length of the beam produces a resultant force of 160 pounds. We are also told that the bars are stacked, quote, about 3 times as high on the right-hand side as the left-hand side, unquote. We are not told how the stacking varies from left to right, only the magnitude of the right side relative to the left side. The figure indicates that the variation is approximately linear, although sometimes the step up occurs after 4 bars and sometimes after 5 or even 6 bars. The way the problem statement is phrased and the way the figure is presented, we should understand that this construction of W of x is approximate. We will begin by representing W of x as W of x equals an as yet undetermined value of line load at x equals 0 times the quantity 1 plus x over 10. Here x is measured in inches, and W0 represents the value of the distributed load at x equals 0 and is something we don't know yet. The functional dependence in brackets is linear and has been selected because it's approximately consistent with the figure and also with stacking about 3 times as high on the right side as the left side for a beam of length 20 inches. You can see that the term in square brackets will turn into 3 when x is equal to 20. We now have to find W0 based on the requirement that the integral of the line load over the beam is 160 pounds. So we have 160 pounds is equal to the integral of W of x dx over the length of the beam. I can pull out the W0, and we're integrating from 0 to 20 inches, 1 plus x over 10 dx. That integrates very simply to x plus x squared over 20, which we're evaluating between 0 and 20. And so we have 160 pounds equals W0, and then the term in the square brackets here will be 20 plus 20 squared over 20, so it's just 20 plus 20 inches. And that gives us that W0 is 160 over 40, or 4 pounds per inch. We now need to find the effective center of this distributed load, which we get from this definition that its effective center is the ratio of these two integrals. We already know the denominator, that's 160 pounds. And so now we'll pull the W0 out in front again. We're going to have 4 pounds per inch on top. integral from 0 to 20 inches, and now we have x times 1 plus x over 10 dx. Again, the denominator here is just 160 pounds. This gives us 1 over 40 inches, and then the integral is going to have units of inches squared, and that integral is simply x squared over 2 plus x cubed over 30, evaluated between 0 and 20. And if we plug those numbers in, we get that this ratio ends up being 1400 over 120, or 11.67 inches. Now our simplified free body diagram is going to look like this. We're built in at B, so we'll have a Bx and a By, and we're going to have a moment. And since the only external load is from this weight, which is tending to induce a counterclockwise moment about B, I'm going to draw the reaction here at B as clockwise. Our resultant force is here, and it's 11.67 inches from this left-hand side. So if I want to find the reactions at B, Bx is just going to be 0, By will just be equal to the weight, it'll be 160 pounds, and taking the sum of the moments about B and setting that equal to 0, I'm going to find that the moment about B, the moment reaction about B, has to compensate for that counterclockwise moment from the weight, and that's just going to be 20 minus 11.67 inches times the weight, which is 160 pounds, and that ends up giving me a value for the moment reaction at B that's 1333 inch-pounds. The previous example is representative of the kinds of problems we'll see in Chapter 8. When we make the transition to mechanics of materials, we'll want to know if that cantilever beam can really support the load without experiencing too large a deflection. A first step is constructing W of x, finding the resultant load in its effective center, and then finding the support reactions. And although this process works for any W of x, it is often the case that the distributed load can be represented as a composite of relatively simple dependencies, uniform or constant, and linear. Here's an example from your textbook where the functional form of W of x could be represented as W of x equals 12 kilonewtons per meter times 1 minus x over 60. We can see at x equals 0, W of x is 12 kilonewtons per meter, and it tapers linearly down to 6 kilonewtons per meter when x is equal to 30 meters. If you like, you can use the integral definitions to confirm that the resultant force is 270 kilonewtons and that its effective center is 13.33 meters from the left edge of the beam. As an aside, note that the reactions to the built-in support are still 2 force reactions and 1 moment reaction, but the notation is a bit different from what we've previously seen. The x component reaction is aligned with the long axis of the beam, and this is called the normal force instead of, let's say, a sub x. The y component reaction is perpendicular or transverse to the long axis of the beam, and this is called the shear force instead of, for instance, a sub y. The moment reaction has a familiar label. It is also transverse to the long axis of the beam, although it's in the z direction instead of the shear force's y direction. This moment is referred to as a bending moment because of the kind of deformation it tends to induce in the beam. These labels reflect different kinds of deformation associated with these different loads and become important both in Chapter 8 and in the transition to deformable bodies in mechanics of materials. But let's get back to the problem and an alternative to performing the integration. As long as the shape of W of x is no more complicated than linear, we can break the distribution into a series of rectangular and/or triangular shapes. The base of the rectangle or triangle may have units of length, but the height has units of force per unit length, so the area of these objects is a force. The centers of these force distributions are the same as the centers of the corresponding geometric objects. It's in the middle of the rectangle, or a third of the way from the base of a triangle. Two different possibilities are shown here. On the left, in A, we have a distribution modeled as a composite of a rectangular shape and a triangular shape. The area of the rectangle is length of 30 meters times a height of 6 kilonewtons per meter, or 180 kilonewtons. Its center is 15 meters from A or B. The area of the triangle is 1/2 times its base, 30 meters, times its height, an additional 6 kilonewton per meter, to get us 90 kilonewtons. Its center is 1/3 of 30 meters, or 10 meters from A. Note that the resultant force is 180 plus 90, or 270 kilonewtons, and we could also perform a force-weighted average of these two forces to evaluate x bar as 180 kilonewtons weighting 15 meters plus 90 kilonewtons weighting 10 meters over 180 plus 90, and that would again give us 13.33 meters. There really isn't a need to turn these two forces into one resultant force. We could just use the two discrete forces as they are to find the reactions directly. Note also that as an alternative, we could model the two force distributions as two triangular distributions as shown in case B. In this case, F1 is 1/2 times its height, 30 meters, times its base, 12 kilonewtons per meter, giving us 180 kilonewtons, and has a center at 10 meters. And F2 is 1/2 its base, 30 meters, times its height, 6 kilonewtons per meter, giving us 90 kilonewtons, now with a center at 20 meters. The resultant is still 270 kilonewtons, and the resultant's effective center is again at 13.33 meters. These representations often provide a more efficient alternative to performing integration. Let's take a look now at another example. This second example is from your textbook. We want the support reactions for the loading shown, which consists of a uniform load on the left half of the beam, a uniform plus linear distribution on the right half, and a single discrete force couple at B. We can model this as a uniform piece plus a triangular piece. And the uniform piece has got its effective center right in the middle. The triangular piece will have its effective center a third of the way from its base. It'll be roughly right over here somewhere. And so we will sketch the free body diagram now, just replacing those distributed loads by their equivalent discrete loads at their effective center. I'll call this load F1 and this load F2. Let's calculate those first. F1 is 40 feet times 200 pounds per foot. That's 8,000 pounds, or 8 kip. F2 is 1/2 its base, 20 feet, times its height, and that would be the difference between 400 pounds per foot and 200 pounds per foot, or an additional 200 pounds per foot. That gives us 2,000 pounds, or 2 kip. Our free body diagram now looks like this. We have a pin support on the left, so we'll write AX and AY. We have a roller support at B, so we'll put just B out here. And we've got this 50 kip foot force couple or moment, so I'll go ahead and add that. We have our force F1, which is 8 kips right in the middle. And we have our force F2, 2 kips. And the center of this is a third away from its base. This distance right here is going to be 6.67 feet. We also have a 1 kip discrete load right in the middle as well. So now our equilibrium equations give us the following. First, we just have AX is equal to 0. Vertical force equilibrium is going to give us that AY plus B is equal to the sum of all these downward forces. We have 8 plus 2 plus 1, or 11 kips. And if we take moments about A and set that equal to 0, we have, from our force reaction at B, we have a counterclockwise or positive contribution of B times 40 feet. Then we have our 50 kip-foot force couple. We have a total of 9 kips acting through the midpoint of the beam, so we have minus 9 kips, because it's a clockwise moment, times 20 feet. And then we have minus 2 kips times 40 minus 6.67, or 33.33 feet. That sum is equal to 0. And if we solve that, we can get B directly from the moment equation and then plug that back into vertical force equilibrium to get A sub y. We end up with B is equal to 4.92 kip, and AY then is equal to 6.08.